Hello students, in this video we will discuss the 8.4 energy conservative force part 2. Okay, and now we assume that all the internal force are conservative. Okay, then the force must be corresponding to a potential energy functions of let's say the particle 1 and 2. Okay, then this force have a corresponding potentials. This is a potentials. Okay, then the rate of working as well be equal to the minus of the rate of this potential energies. Okay, then the rate of working, this is the rate of change of the working is equal to, this is also the change in the earth's position, and the force is like constant conservative, is equal to the minus of this TB divided by dt. It's the change as the rate of change of the earth's potential energy. Okay, and let us this potential energy is the sum of the potential energy for the, let's say there is the number of particles, then there is exist a number of pair. Okay, and let's say this pair is n into n minus 1s divided by 2. There is the number of pair of particle, there is a pair of particles. Okay, now let's say for n is equal to 2, then there is only one pair, because this and this, only this pair is possible. I mean, put here, then this is 2 and 2 minus 1 divided by 2, this is 1. Okay, and when the n is equal to 3, then this is 3 and 3 minus 1 divided by 2, and this is equal to 3. When n is equal to 4, then there is 6 pair. Okay, now then the rate of working of all the internal force is will be the minus of the rate of change of the earth's internal potential energy. Okay, then we know the total energy is equal to kinetic energy plus the earth's internal energies, internal potential energy is equal to the total energy, but we can write here is to the earth's works. Okay, this is also energy, the work is also energy. Okay, but then we can write work, then the T kinetic energy and plus the internal potential energy, and this is equal to R dot, this is equal to R dot F. Okay, this is only R dot F. Okay, then the rate of change, the kinetic energy and plus the internal potential energy. Okay, this is the rate is equal to the rate at which the external force do work. This is the external force, this is R dot and dot F. This is the rate of change of this total potential, the total kind of energies. Okay, then the rate of change of the kinetic energy relative to the center of mass is the total the kinetic energy relative to the center of mass is like this. Okay, then we take the derivative, this is d divided by dt, and then this is 1 half capital M, the M is constants, and then we take the derivative of R dot square. First this is R dot, and also the derivative of the R dot is R dot or double dots. Okay, this 2 is cancelled to this, then this is equal to M R dot and R double dots. Okay, and also we can write is R dot F, and this is M R double dots. Okay, then the R dot and dot, this is the is equal to the R dot double dot is equal to this the sum of the its forces. Okay, and then this is the summation of the Fi. Okay, now this is equations 1. Okay, and this is the equations 2. Now we subtract the equations 1, okay, from equations 2. Now then we can do this as d divided by dt, okay, and 1 over capital M R dot square and minus t divided by dt and t plus V internal potential energy, okay, is equal to this is R dot, this summation I the Fi, and minus the summations of the R dot I and Fi. Okay, then we know this is the kinetic energy. This kinetic energy is equal to 1 half capital M R dot square. This is the relative kinetic energy, and this is the relative kinetic energy to the center of mass. Okay, and then we put here, then this is d divided by dt and minus, we put here d divided by dt as 1 half capital M R dot square plus t plus, and then the internal potential energy is equal to this. This is the and here we take the summation of F is summation of Fi as equal to R dot minus R dot I. Okay, and then this term is cancelled to this term. Okay, and then we can write t divided by dt of t plus and V internal potential energy is equal to the sum of the Fi of R dot minus R dot I. Okay, and we know the Ri is equal to R plus R plus I. Okay, and then we take derivative, okay, and then we rearrange these equations. Then this is equal to R plus I is equal to R dot I minus R dot, and then we put this value in here. Then d divided by dt of t plus, and this is the relative kinetic energy about the center of mass, and this is the internal potential energy is equal to sum of the forces Fi, and this is equal to this is R plus I. Okay, and where the potential, the internal potential energy, okay, is the functions of only of the taperness is Ri and Rf or Rj, okay, and unaffected by the reference poems. Okay, now we suppose that the external forces are also conservative. Okay, and first we consider the internal potential, and now we consider the external potentials. Okay, and we say that the external forces are also conservative. The external forces are also conservative. Then there is must also exist a corresponding external potential energy, which is the V externals. Okay, there must be existed. Then whose rate of change is the minus of the rate of working of the external force. Okay, then we can write these equations as well as there is external potentials also. Then we can write these equations like this. This is T divided by dt as total energy and plus the total potentials. The total potential is the V internal and V externals. Okay, is equal to the summation of Fi and Ri plus. Okay, and there is no plus. Okay, now then we can write these equations as T plus V is equal to the summation of I and Fi and Ri. Okay, is Tt. Okay, then we integrate both sides. Then we can write this is T as T plus V is equal to the integration of the summation of I and the Fi R dot I. Okay, and to dt, then this is cancelled to this. Now this is T plus V is equal to, and then we can write this is R dots. Okay, and then this R dot is can be write like this. Okay, this is cancelled to this and this is cancelled to this. Then this is T plus V is equal to the sum of the forces of the R dot I, and this is the work, and here we put the work is equal to the its energy. And then and in the starts, okay, we put the total, the energy is equal to the works. Then this is the equal to the its energy, and this is constant. This is the law of conservation of energy. Okay, and where this potential is the external potential and plus the internal potentials. Okay, and the external potentials, okay, is depend on the coordinate themselves, but not on the coordinate difference, which is depend the internal potentials. The internal potential is depend on the coordinate difference and not depend on the prime of reference. Okay, and there is also the choice of the frame. This also depends. This is the unlike the case of the internal potentials energies. Okay, thank you.